Okay, here's an example of orbital motion which involves conservation of energy, something you're already familiar with. Um, Basically, the comet's going to exchange kinetic energy for greater potential energy as it moves along its orbit. And so this is the point of closest approach that they're talking about in the problem. So they're talking about that at the closest point to the star, the distance r initial would be the 7.75 times 10 to the 10th. So that's the initial point in the problem, and it's going to have an initial velocity at that point of 71 kilometers per second. Okay, so this will be related to its potential energy, and this would be related to its kinetic energy at that point. And then sometime later, they're asking about at what final height or distance away from the sun would it have a velocity of 68.5 kilometers per second. So this would be, for instance, its final velocity. Since it's only energy that we're going to have in our system and there's no external forces acting on it or no non-conservative forces, basically we can use the law of conservation of energy to solve the problem. So just label everything that you know and don't know. And remember our term for kinetic energy is 1/2 mv squared. Our new term for potential energy for gravity in this problem is negative g, the mass of each object, over r. And that has to do with the fact that the force varies with r. And this becomes the new term that we use for gravitational potential energy. Okay, so as we set up the problem, you're used to seeing this term, and you're going to be able just to substitute symbolically in our values. And the big difference is you have to make sure you keep this negative sign in here for the final potential energy minus the initial potential energy, also with that negative sign. All right, it's important to keep that in there. Now here on out, it's really just a matter of algebra and being very careful with your calculator and tracking the numbers. Notice that the mass of the comet, the object which is orbiting, is common to every term. So that's going to cancel out. All right, that'll cancel out of each of our terms here, 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 and here, which leaves us with this expression. Now, probably the easiest thing at this point to do um, is to substitute in. You could go ahead and solve this for that final position if you'd like to. Otherwise, go ahead and put some numbers in at this point. It might help clean up the problem for you while you're learning how to do these. And remember that you want to express the velocities. They were given to you in kilometers per second, so we're going to put those in meters per second. This would be the final velocity out at the position further from the star was 68.5 times 10 to the third meters per second here. Initially closest to the star it was 71 times 10 to the third meters per second. And then we have our expression g. We have the mass of the sun, which was given in the problem, 1.99 times 10 to the 30th kilograms over the final position. Two negatives, so we have a plus term, our expression for our final or our initial potential energy when it was closest to the star. Here's the values that I get when I calculate this out, and then I combine all my numerical values together, which leaves me with this kind of final algebraic expression. Then when I solve for RF, when I solve for RF and do the math, being careful of my order of operations, I end up getting for my final position here, my final distance from my star, 8.63 times 10 to the 10th. So we've lost speed, essentially, all right, from 71 times 10 to the third meters per second down to a speed of 68.5 times 10 to the third meters per second, but we've gained height, all right? We've gone from a position of 7.75 times 10 to the 10th meters closest to the star, now out to a further position of 8.63 times 10 to the 10th meters. So that's one of the ways you apply the law of conservation of energy to orbiting objects.